Hello, my name is Eun-Suk Jeong. Today I would like to give you the SAPS experiment and SAPS theory. XAFS theory. Let me give you the outline of this lecture. First, the synchrotron will be addressed for comprehensive understanding. Next, the overall SAPS setup will be demonstrated. As you know, there are two measurement modes for SAPS. Transmission mode and fluorescence mode, so they will be explained in detail. Before taking such experiment, we carefully prepare the sample. So I want to explain how to prepare the sample. A simple procedure of substrate measurement will be introduced, and I will suggest important remarks of substrate measurement to get good data. Finally, the substance theory will be derived from the simple idea. First, the substance experiment will be described. Before telling the substance experiment, let's look around the synchrotron. The general synchrotron consists of a linear accelerator, booster ring, storage ring, and experimental hearts. From the synchrotron, we can get the high flux, wide energy, high brightness, slow pulse, and high polarization. Look at this picture, which is my laboratory in front of a synchrotron PLS 10C house in Korea. The person in the pink circle is me. The other picture is the inside of the heart. In the early 1970s, Sayers and Leiter installed the spectrometer for such experiment in the Stanford Linear Accelerator Center. This is the first generation synchrotron. In 1980, the second generation synchrotron was built at the storage ring with a bending magnet. When the electron change their direction by bending magnet, the X-ray is generated. Okay? In 1990, insertion devices such as Wiggler insertion device and undulator devices were fabricated, and they were utilized to make a higher flux and density and coherence X-ray. The synchrotron with insertion devices is the third generation synchrotron. In the Wiggler and undulator insertion devices is the In the Wiggler and undulator device insertion devices, the permanent magnetic poles are arrayed in turns as shown in this picture. The electron or the positron with the velocity with the velocity similar to the light pass through them, so we can get X-ray with a high flux, high energy, and high coherence. To get significantly stronger coherence X-ray, long undulator insertion device is used, as shown in this picture. This is called fourth generation synchrotron or X-ray free electron laser. Now let me explain experimental experimental setup. This schematic demonstrates the SAPS experiment. When the X-ray is generated from the synchrotron, it goes to the double crystal monochromator, which is made from the single crystal such as silicon or germanium. The first crystal selects the X-ray we want, and the second crystal adjusts the beam line. After double crystal monochromator, the X-ray passes through the slit and anode chamber and meets the sample. The scattered X-ray goes back to the fluorescence detector, and the penetrated X-ray goes to the transmission chamber. Therefore, we can get the subs data with the transmission mode and fluorescence mode. Look at this picture. The picture is the image of an experimental setup. This is anode chamber. This is our transmission chamber, and this is a fluorescence detector, which is a silicon detector, and here is a sample. So the X-ray left to right. We can also measure the reference as the reference materials is put between I transmission and I reference chamber. From now on, I'm prescribing transmission mode and fluorescence mode in detail. First, to address the transmission mode, look at this figure. This is the sample with X thickness. The intensity of incident X-ray and transmitted X-ray are I naught and I tier respectively. By the Bureau, I transmission intensity equals to I naught exponential minus mu x, where mu is the absorption coefficient. Therefore, the total absorption coefficient there is natural log I naught over IT. The Beer's law applies to I naught chamber, I transmission chamber, and the sample. The chamber, I naught and I transmission are filled with helium, argon, or mixed gas. The absorption coefficient of I naught chamber and I transmission chamber are decided as controlling the amount of gas because the length of the chamber is fixed. Before the subject experiment, you must check the gas with the operator in synchrotron. Generally, the amount of X-ray absorption in the chamber is controlled to have 5 to 25% of initial intensity. Okay, look at this picture. This which is the transmission data. As increasing the energy, the absorption cross-section gradually decreases, so the total absorption coefficient also decrease like that. Now we have a question: how can we get good SAPS data in transmission mode? Right? Before I talk about condition to get good SAPS data, I'd like to deal with the sample preparation, which applies to both the transmission and fluorescence mode. First, we must prepare sample with uniform thickness. Okay, it's wrong, it's right. And next, we have to prepare sample with uniform density. Okay, and then the good SAPS data are obtained when the absorption coefficient, when the total absorption at this step is greater than 0.2 and 1.0. If the total absorption step is greater than 1.2, the SAPS data are distorted by self-absorption. If it is less than 0.05, the SAPS to measurement error is very low, so that we can't distinguish between the data and error. When the total absorption at this step is greater than 1.0, we decrease the thickness of the samples. If the total absorption step is less than 0.2, we have to plausible problems, low concentration or thick thickness. And the low concentration increase the thickness, and the thickness decrease the of the sample. Decrease the thickness of the sample. Okay. Also, first, the cross section of X-ray is less than that of the sample, and finally, the thickness of the sample is less than unit absorption. Okay. Now let me explain fluorescence mode. Okay, look at this figure. In fluorescence mode, the incident X-ray with the inerts goes into the sample and it is scattered with the IF. The T is the thickness of the sample and G is the penetrated depth. dG is the layer of scattering atoms. Theta I and theta F are the angle of incident and scattered X-ray, respectively. From Hans' paper, IF equals to this equation, where epsilon is total fluorescence efficiency, mu T is total absorption coefficient, which includes electron coefficient and background coefficient. When the electron coefficient is much greater than background coefficient, the total absorption coefficient is similar to the electron coefficient. And then the thickness of sample is very thin, and the atomic total coefficients are ignored. We can get the total absorption equals to these equations. From the normalizations, we can cancel this factor. Even though this equation has been known as the fluorescence formula, generally, we have to consider the thickness and background. Therefore, to get good SAFS data in fluorescence mode, first, the thickness of the sample is less than unit absorption length, like transmission mode. And second, the background coefficient is ignored when we use good data and good detector, such as silicon germanium detector, or like that. And then the background coefficient is the fluorescence from other atoms besides the target atoms. So the longer the penetration depth, the greater background coefficient. So we must consider the thickness of sample in fluorescence mode also. From previous formula, you can get this formula, which is the general fluorescence SAFS. Total absorption of energy is proportional to IF over I0. When you use the proportional constant C, we can make this equation, and then that equals to mu naught 1 plus chi, which chi is the SAFS. The SAFS is different from XRD. We detected the scattered X-ray in front of the sample like this figure. Okay. The fluorescence mode is good for low concentration materials, very thick samples, and amorphous materials. However, it has many problems such as Compton scattering, bragg peak, background coefficient from other atoms. Yeah, look at this figure. This is the fluorescence zinc oxide cobalt SAFS. In contrast to transmission mode, the X-ray signal increases as an energy. Because the increase in the X-ray energy, the penetration depth is also elongated. So the total fluorescence is increasing because the background coefficients are increased. There are several extra peaks in the figures. A strong peak. Look at this strong peak. Probably strong peak may be from the bragg peak, and others may be from the background. Generally, fluorescence data can contain more errors than transmission mode. Therefore, fluorescence data are carefully collected. And now, we take an effort to minimize fluorescence problems as following these. First, The angle of detector can be changed to avoid black peak, or the filter in front of the detector is used to avoid the background coefficient from others. And second, preparing sample with the thickness less than unit absorption length. And third, using the detectors to remove background fluorescence, such as solid-state Jeong detector. Okay. Before taking such experiment, we must carefully prepare the sample. I will tell you about the preparation of the powder sample. The sieve with 20 micrometer mesh, the fine brush, a bowl, scotch tape, and slide glasses are prepared. First, the powder are grinded in the bowl and filtered by the sieve. The scotch tape is put on the base of slide glasses like that. This is a base slide glass and scotch tape. This is the top view. Two side glasses are laid on the side of scotch tape. Yeah. And then the filtered powder are spread out on the scotch tape using the fine brush. After making uniform atomic layer on scotch tape, the scotch tape is folded like that. The scotch tape is cut as what you want to make a proper thickness of the sample. If you want to take such experiment in high temperature as gas and electric field, you would better make the fillet to mix the other materials. To make the fillet, you choose the materials which doesn't affect your samples. In our case, we use the boron nitride. And the And the boron nitride is mixed with our samples. Mixed powder is put into the hole of the sample holder and pressed, so we can make the fillet. Now, let me tell you about procedure of SAPS measurement and remarks. First, the SAPS experiment can be described as 4 steps in brief. First, you calibrate E naught, which is the energy of probed atomic orbital in the samples. So put the reference foil or the reference materials on the sample stage and control the motor of double crystal monochromator. After finding E naught, you make detuning, which is the process to find the first order X-ray. Next, I will address the detuning process. Now, you change the reference to, after detuning, you change the reference to sample and you start to scan the stops. Before scanning the stops, you need to take the dark current and check the extra beam error. Finally, start to scan 3 times per 1 sample. Strongly recommend you make 3 times scans per 1 sample. And next, we have several remarks when we take the SAPS experiment. First, you make 3 scans per 1 sample if possible. And second, use both modes, transmission mode and fluorescence mode if possible. Third, use the reference foil or reference materials as measuring samples. Fourth, the photon count must be greater than 3 times 10 to the 4. Try to increase due to decreasing statistic error. So whenever taking those steps, you have to check the photon count. Okay, it's very important. If the photon count is less than 3 times 10 to the 4, try to increase it using detector gain, uh, slit size, integration time, or adjusting the thickness of the sample. Fifth, in transmission mode, the total observation at this step should be greater than 0.2 and less than 1.0. Finally, in fluorescence mode, you need to check whether the sub-signal has noises or not. Let me describe the tuning process. After inert calibration, we must make a detuning process. The detuning process is to remove high order frequency mode. Look at this figure, which is a double crystal monochromator. The double crystal monochromator consists of first crystal and second crystal. And the X-ray contains various frequency, right? So when the X-ray with various frequency goes into the first crystal, the unique X-ray is selected by the Bragg law, like this. Yeah, this is the Bragg formula. So, however, the X-ray at Bragg angles theta contains high order frequency X-ray and fundamental X-ray. So, I mean that the X-ray with the maximum instant intensity. The X-ray with the maximum intensity has fundamental frequency and high order frequency, like this figure. This is example lambda 1. This is a high order frequency. To get the monochromatic wave, we have to avoid the maximum intensity. So, in the process of detuning, first you rotate the double crystal monochromator to find the maximum intensity. After finding the maximum, rotate the double crystal monochromator back by the 70% of the maximum intensity right there. Therefore, you can remove high frequency mode, so you can get the monochromatic wave. Okay. I highly recommend the 3 scans for one sample and using the reference point. Okay, let me explain the regions. Look at this figure, which is the subs of silicon nitrate solutions in fluorescence mode. That time you have 3 scans. As you see, there are some noises after 6 inverse angstrom. So, what is the good subs data? If you take just 1 scan or 2 scans, you are not able to find the answer of my question. When you take 3 scans, you can know where the noises or errors come from. Okay. Second, look at the chance of platinum foils, which is the same sample but different edge, right? Surely, a platinum foil is a very stable material, so it's this chance has the problem. So what is the problem? The problem is that the first crystal in the double crystal monochromator can be offset. So the main edge is shifted because of that. The main edge of all subs for my samples are also shifted. When you analyze the genes, we have to shift the samples as the platinum foil, like that. Therefore, I strongly also recommend the 3 scans and using their reference. Until now, I have addressed the subset measurement. From now on, let me derive the substance theory from simple idea. This is the theory of subs, which I explained in the last part of first lecture. So I will derive this theory now. Yeah, look at this picture, which expresses the photoelectron wave generated by the X-ray. So, yeah, this is outgoing photoelectron wave, and this is a backscatter photoelectron wave. And then the neighboring atom is located at Ri. The interference wave at R, this part, wave, which is psi, is proportional to Ti times the outgoing wave times backscattered wave, where Ti is backward scattering amplitude characteristic. Because interference wave affects the X-ray at R equals 0, so R is cancelled. Yeah, right? Considering phase shift, the number of neighboring atoms and real part of wave, we can get this equation. This is a phase shift for phase shift, and the summation is the number of neighboring atoms. The lifetime of a whole and excited electron is added by proto-electron mean-free path, lambda, so we can get this equation. Okay. The absorption coefficient can be expressed by Fermi-Golden rule like these equations, psi f and psi I. So the psi f, the final state, equals to psi outgoing wave and psi backscattering wave, which is this wave. All atoms are not exactly located at the same distance. When we distribute the bond length, the cumulative expansion is added. So look at this sigma square. The divider factor sigma square includes the thermal vibration and static disorder. Finally, the polarization of instant X-ray and the effect of the presence of a whole exoscale are considered, so we can get the XAFS theory like this equation. I would like to stress memorizing these equations when you learn and analyze. Now, I would like to tell you about the procedure of subs analysis. We will use the Demeter software, which is based on the IFFE software when we analyze XAFS. When you download the Demeter and install, you can get the Athena program and Artemis program. Athena is the program to remove the background and to analyze the GENS spectra. The Artemis is the program to feed data to model. Athena program includes the AutoBack code to remove the background. And using AutoBack code by this formula, we can get XAFS of K and X or XAFS of R after Fourier transformation. Meanwhile, Artemis contains three program atoms, PEP and PEPID. Atom is the program to generate PEP from the crystallography information, and the PEP calculates the contribution of the atomic pairs around a probed atom. And then the peptide makes a fit between the data and the theory, which is calculated by PEP. Okay, so during the data fit, you have to use this formula. Okay, I finished this lecture, and thank you for second lecture. I hope my lecture helped you. Goodbye, and see you next lecture.